Welcome to this video titled An Introduction to QoS. In this video, I'm going to answer the questions: what problems are solved by QoS? Why would we use this? How does QoS control traffic? And we're going to look at the day in the life of a packet from the perspective of a router and two different types of switches. We're also going to look at the differences between buffers and queues. So let's start with an overview of QoS. With any acronym, the very first thing we need to know is, what does the acronym actually stand for? QoS stands for Quality of Service. Now, what problem does it solve? It provides predictability of management of network resources during times of congestion. Let's break that down. So, when we think of an interface, any interface, whether it be a fast Ethernet, a gigabit Ethernet, a serial, whatever it is, and whether it be on a router or switch, one of two things can be true of that interface. Either that interface is congested or it's not. If it's not congested, that means that as packets are going through that router or switch, being directed to that interface to be transmitted, there's no delay. There's plenty of bandwidth, there's plenty of room, so as soon as those packets or frames are sent to that interface, they're immediately put on the wire and out they go. So that's our perfect scenario. And in a perfect world, when you think about the packets as they leave your laptop or PC, all the interfaces they have to go through to get to the destination, in a perfect world, there wouldn't be congestion anywhere along that path. So those packets would get to the destination as fast as possible. There would be no holdup, no delay, and certainly none of your packets would be dropped. However, that's not always the case, because a lot of times, as an interface is getting your packet to be transmitted, it has lots of other packets from other sources that also need to be transmitted out that exact same interface. So imagine a situation where a router or switch has 10 or 15 different interfaces are all receiving packets at the same time, and all those packets are being directed out one common egress or transmit interface. Well, if so much stuff is coming in at a rate that the transmit interface can't transmit those packets onto the wire fast enough, now we could have congestion, where the transmit interface says, okay, since I can't get them on the wire fast enough, I'm going to start buffering or holding back these packets in memory, in queues, and then put them out on the wire as I can if I can catch up. But if he can't catch up and those queues end up getting full, now we have to end up dropping stuff because there's no place left to put them. Now, without QoS, every packet is seen as the same by a router or switch. For you as a human being, certain packets might have more or less priority. Maybe your IP phone packets have a higher priority than your web browsing packets. But to the router or switch, without QoS turned on, and QoS is not on by default, every packet is seen as the same. So if a memory queue starts getting full, packets are going to be delayed, and it could be your voice packet that's delayed, could be your data packet that's delayed. If memory queues get completely full and stuff has to start getting dropped, once again, completely random, completely uncontrolled as far as what will be dropped. So quality of service provides some predictable management during those times of congestion. So for you as a human being, it assists in maximizing your end user experience of your critical sessions. I mean, after all, if there's going to be some delay in the network somewhere because some queue is getting filled up because an interface just can't put the bits on the wire fast enough, wouldn't you prefer that that delay happen when you're trying to download some web page like google.com or something versus a delay in your IP phone conversation where you're talking to your customer? QoS will help you manage that. And it provides differentiated services to packets based on predefined user criteria. So part of QoS is that you as a network administrator or network engineer, you have to get onto that router switch and you have to take what's in your head, like voice is more important than data. Video is more important than data. You have to take that and convert it into QoS features and commands so the router or switch knows what you're thinking. It knows how to classify and categorize traffic like you want it to. So how does QoS do this? How does it control network traffic? Well, there's a lot of different QoS features, more than any one person could ever possibly know. And now some of those features are designed to accomplish a very specific task Other features, when you turn them on, can accomplish 2 or 3 things at one time. So when we talk about the various tasks at a really high level of what QoS can do, we can break it down to about 5 or 6 different things or categories. Number 1, there's classification of data. This is what I was just describing when I said, hey, you need to turn on some feature that will recognize voice, that will recognize video, that will recognize data and be able to distinguish between them. Whatever that feature is, we would call that a classification feature. There's also queue management. So as my interface is saying, hey, I can't put bits on the wire fast enough. They keep hitting me on the back of the head and I can't get them on the cable quickly enough. I need to put those bits into a memory called a queue. Well, there's QoS features that talk about how do you do that and how do you manage that queue. Such as, how do we control the size of the queue or the placement of packets, the scheduling order, the transmission rate. There's QoS features that deal with all of that. There's something called preemptive queue drops. This is another type of QoS feature that you can turn on. That you can say, hey, look, this memory queue that you have that's filling up with packets because you just can't get them on the wire fast enough. Well, maybe what we want to do as packets are trying to get into that memory queue, if they're low priority, maybe we should just preemptively drop those so we always reserve a little bit of room in that queue for our higher priority traffic, like our voice. And there's also the marking of packets. There's a difference between, as packets come in, being able to identify them based on protocol or application or the nature of the packet, how it behaves, versus putting a label on that packet, like a simple number, like 1, 2, or 3, and then having subsequent network devices like subsequent routers and switches being able to just look at that marked number to make their QoS decisions. So placing that number or that label on a packet is what's called the marking of packets. Now, a vast majority of what these QoS features do has something to do with memory, the manipulation of router or switch memory. And so we have to be aware of the differences between something called buffers and queues. So a buffer is the physical memory used to store packets both before and after a forwarding decision is made. As it says here, on routers, the same memory can be allocated to interfaces as interface ingress or egress queues. Now, shared memory, which is part of allocate buffers, is also used by a lot of other CPU processes. So let's talk about this for just one moment. Imagine for a moment here that I have my router, and here are his interfaces. Just a few interfaces down here, maybe a fast Ethernet interface, another fast Ethernet, maybe a serial interface. Now that router also has a CPU, which is his brain, and he has some physical memory space. So this is a physical memory chip right here. And each one of these squares inside here represents a memory cell, a location where he can store a 0 or a 1 as an electrical charge. So all of this would be considered my memory buffers. So it's my physical memory. And the CPU, when he boots up, when this router switch boots up, he's going to decide how to carve out or allocate these buffers. He might say, okay, this part of the buffer is right here. I'm going to use for storing my routing table information. This part of the buffer is right here. I'm going to use to store maybe my OSPF link state database if I'm running OSPF. And maybe this part of the buffer is right here. I'm going to use as my interface buffers. Those will be my interface buffers. Now, without QoS turned on, without QoS enabled, the router is basically going to say, okay, of my interface buffers, I'm going to take maybe this section right here, and I'm going to allocate that for one of my interfaces. That'll be my transmit buffer for fast Ethernet 0/0. So as packets come in, and if they have to be transmitted out, fast Ethernet 0/0, I will store their 1s and 0s in this section of memory right here. Now without QoS, we've got this physical memory here for fast Ethernet 00, but anything that's put in there is treated equally. In other words, whatever goes in there might be voice, it might be video, it might be data, but the router switch doesn't care. It's first in, first out. And if that thing starts getting full and ends up having to drop stuff, there's no telling what's going to be dropped in there. It's just completely random, first in, first out. That is what's called a buffer. Now, what's the difference between a buffer and a queue? Well, when we turn on quality of service, now we can manipulate that buffer. We can say, hey, that physical space, that physical buffer that was allocated for fast Ethernet 00, now we turn on QoS, why don't we carve it out into like some logical spaces? In other words, maybe right here was that buffer space that was allocated for fast Ethernet 00, so this is part of the larger physical memory chip. But with QoS turned on, we can say, hey, why don't we logically carve that up into some subsections? Like, why don't we say this part of the buffer space here, we're going to call it the low priority queue. And then why don't we take another buffer space right here, and we'll call this the medium priority queue. And then why don't we take another part of the buffer space, like maybe this section right here, and call this the high priority queue. And with QoS, we can dictate or determine which packets are placed into each one of these sections. Furthermore than that, once we dictate with QoS which packets, for example, go in the low priority queue, we can determine how those packets will be serviced. Will that queue be completely emptied out before the medium priority queue is even looked at? Or will we maybe service 5 packets from the low priority queue, pause that queue, move over to the medium priority queue and service 10 packets from there, pause that, and then move over to the high priority queue? You see, without QoS, this was just generic memory buffers, first in, first out. But with QoS turned on, we can now view that memory buffer from a logical perspective of dividing it up into these queues, and we can control those queues. So that's the difference between queues and buffers. All right, so let's take a look at the day or a day in the life of a packet as it moves through router and 2 different types of switches. And so we can get a better feel for how these buffers and queues are utilized. All right, so step number 1. A packet arrives on an ingress interface. Now, the moment that ingress interface starts detecting the bits coming in, it detects the electrical energy, or if we're talking about a fiber optic interface, it starts detecting the laser light and the different frequencies of light, it's able to say, ones and zeros are coming in. The moment that happens, those ones and zeros have to be stored somewhere, and so they're put into physical memory buffers, and we call this the receive ring. Okay, so the receive ring is simply a memory buffer that's accessed via direct memory access. In other words, as soon as it comes in, whatever the physical electronic components are that make up that interface, those electronic components have direct memory access to the buffers where it can store these ones and zeros as they're coming in. So this is what we call the receive ring. All right, so now the packet is queued in a memory buffer. It's being stored in there. We had to wait till the whole thing came in from beginning to end. And now a forwarding decision is made. So typically speaking, once something's placed into the receive ring, now there's some process that goes to the CPU and says, hey, knock, 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 CPU, I've got something over here in memory cell locations, 145A through 145C. I need you to take a look at this. So now the CPU will pause whatever it's doing, and it'll start the IP input process. It'll say, okay, let me look at that memory. Oh, okay, right here in this block of memory, here's where the destination IP address is, or if we're talking about a switch, the destination MAC address. Let me go look it up. So now a forwarding decision is made, which involves, should I forward this packet or should I drop it? Should I translate it via NAT? What should I do with it? And then the last component of that is, where's this packet going? Is it going to be forwarded out fast Ethernet 00 or gigabit 11? Now, once we determine the outbound or egress interface, now that packet will be placed onto the hardware transmit ring. Now, this might not actually mean physical movement of the bits. You see, when those bits came in, and we're talking about maybe thousands of bits just for one single packet or frame, when they came in for a few microseconds, all those memory cells that were accessed via direct memory access, those memory cells were saying, okay, we're gonna classify these as part of the receive ring for, let's say, serial 1/1. That's where they came in, the receive ring. Now, once the forwarding engine has determined, all right, that string of bits making up that packet, those need to go out fast Ethernet 00. Part of the CPU's job will say, okay, those same bits, you can stay where you are. We don't have to move you. But those memory cells, we're now going to recategorize it as part of the transmit ring of fast Ethernet 00. So you see what we did there? We didn't actually move them. They stayed right where they were. We just sort of looked at those memory cells differently. They're now part of the transmit ring of the egress interface. Or sometimes they're actually physically moved. They're taken out of those memory cells and put into another section of memory cells, which is the transmit ring for the egress interface. And then they're transmitted onto the egress media. They're put out onto the wire. Now, what about a switch that does shared memory? Now, with switches, let me just draw something here real quickly. Switches are broken down into sort of, at a high level, two different types of architectures. We have shared memory and we have distributed memory. This slide is talking about shared memory. The next slide is going to talk about distributed memory. Here's the main difference. So here are my interfaces, all right, of my two different types of switches. And we have some sort of ASIC, application specific integrated circuit that's controlling these interfaces, that's in charge of receiving bits off the wire and transmitting bits onto the wire. And it might be, like I've drawn here, it might be that several interfaces are shared among a single ASIC. Sometimes on higher end platforms, each interface will have its own dedicated ASIC. But from the perspective of memory, that's kind of irrelevant. So here's the difference. In a shared memory architecture, and let's say that we also have another ASIC, which is our forwarding engine. I'll just mark it as FE here. So he's the workhorse that's going to figure out what to do with a frame or a packet and where to send it. That's the forwarding engine. All right, now here's the difference. In a shared memory architecture, when a frame comes in, it's forwarded to a big block of shared memory up here. So like maybe this portion of memory right here might be allocated as ingress memory or receive memory for a particular port, maybe fast Ethernet 0/1. But it's just part of a big block of memory. So this memory is shared among multiple interfaces. In a distributed memory architecture, each interface has its own memory. So as a frame comes in, that interface has its own dedicated buffers that it doesn't share with anybody else. They're allocated just for that. So that's sort of the high-level differences between shared memory and distributed memory platforms. So right now, let's look at how a packet moves through a switch in this one right here, which is a shared memory allocation or shared memory architecture. So the packet arrives on the ingress interface. Whatever interface or module ASIC that's controlling that physical port, he will immediately forward the packet, like it says, into a common shared memory pool. At that point, the bits will stay in that memory pool, but some of those bits will be extracted or copied and sent to the forwarding engine. After all, the forwarding engine doesn't need to see everything necessarily, right? An Ethernet frame could be almost 10,000 bits long. But of all those bits in that Ethernet frame, the forwarding engine doesn't care about most of it. The data, forwarding engine doesn't need to see that. He just needs to see the bits corresponding to like the destination MAC address and the source MAC address and maybe the Ethernet type code. And if we're talking about a multi-layer switch, he needs to see some bits behind that corresponding to like the source and destination IP addresses. But all that stuff there is like a minuscule portion of the frame. Most of the frame is the data, and the forwarding engine doesn't care about that. So we'll take all the bits of the frame and we'll copy just the relevant portions and send that to the forwarding engine so he can decide what to do with this thing. That's what's happening here in step number 3. So the forwarding engine makes his decision about what to do, and then at that point, the memory ownership of the packet buffer is transferred to the egress interface. This is like what I talked about in the last slide, where we say, okay, all you memory cells, before we did our lookup, you buffers right there, you were the receive buffers for fast Ethernet 01. Now the forwarding engine comes back and says, hey, that frame, that needs to go out gigabit 00. So now there's going to be some memory manager. There's some other background process that's in charge of that shared memory and in charge of determining each cell what its meaning is right now. That memory manager will now say, okay, you memory buffers, you're no longer part of the receive queue for interface fast Ethernet 01. Now we're going to redefine you for a few microseconds as the transmit buffer or the transmit queue for gigabit 00. And then the packet will be transmitted onto the egress media, and away it goes, and now those buffers are freed to be reallocated or reassigned to something else. So that's shared memory. In a distributed memory platform, it's very, very similar. The packet arrives on the ingress interface, but in this case, the ASIC that's controlling that interface has his own dedicated memory. He doesn't have to share it with anybody else. Now, once again, some information, some bits are extracted or copied from that, like the MAC addresses, the IP addresses, sent to the forwarding engine, where a decision is made. The forwarding engine will send his result back saying, okay, that frame needs to go out here, gigabit 11. Now the packet will be put onto something like a shared bus or maybe a shared ring that all the port ASICs connect to. There it goes. In the front of that packet will be the lookup result. Hey, this packet here I'm putting on the ring or I'm putting on the bus, this needs to go to you, gigabit 11. This is yours. And now that egress interface will get it, put it into the appropriate egress queue, schedule the packet, and away it goes for transmission. So in all of this, we haven't talked about congestion. In all of this, as the packets have been put into the queues or the buffers, we've looked it up right away, sent it out on its way. But if egress traffic cannot immediately be transmitted out the transmit port, now what we have to do is place it into an egress queue. So that little memory buffer where it's been stored, we can't empty it out right away because there's other memory buffers in front of it that are still waiting to be transmitted. So now the memory manager says, okay, I need to now rethink about this memory buffer here and call it something else as an egress queue. So without QS, the queue is just one large block of memory, just one buffer. First in, first out. We don't know what's going to happen to the bits. With QoS, we can control the characteristics of what happens to those bits as they're waiting to be dealt with. So what is affected by QoS? So in this last slide here in the presentation, in this particular video, what types of things can we control or manipulate when we turn on these various QoS features? Well, we can manipulate bandwidth. We can say, okay, this queue, you're allowed to transmit at 5 megabits per second only. This other queue, you're allowed to transmit at 10 megabits per second. Because remember, when we turn on QoS, my physical interface here, here's my physical port, fast Ethernet 0/0. Here's the memory buffers that are allocated to him on the transmit side. Now, without QoS, as stuff is put into the memory buffer, hopefully it'll just be sent out. And that's a fast Ethernet interface, so he's going to go at 100 million bits per second. That's what his speed is. We can't slow him down. We can't speed him up. That's how fast he goes. But with QoS, we can now subdivide this into queues, like a low priority queue, like a high priority queue. And now we can affect bandwidth. We can say, okay, we know the fast Ethernet interface is 100 million bits per second. Why don't we divide that and say low priority queue, you can get 40 million bits per second. High priority queue, you can get the rest, 60 million bits per second. So that's something we can do with QoS, is we can affect the bandwidth of how bits are going to be transmitted. We can affect delay. We can say, now that we've divided into queues, if there's going to be any delay anywhere, we would prefer the delay happen with the stuff that's in the low priority queue. Stuff that's put in the high priority queue, you get to the front of the line, you get out first. We can affect jitter. Now, delay and jitter are both very, very closely related. They both have to do with delaying of packets, but here's the difference. So let's take a voice call as an example. You've probably experienced delay with a voice where you say hello, and then you have to wait like a second before your hello gets to the other end of the phone line, especially if you're talking to somebody on another continent. So with delay, with an IP phone, when you start speaking, it starts translating your voice into IP packets. And each one of those IP packets has a little bit of delay in between them, but the delay is evenly interspersed. In other words, if you were to look at those IP packets with a timestamp, you would see the delay when packet number 1 was transmitted, then packet number 2, packet number 3, it was all equal. Hopefully it's very, very small, but it's all equal. So if that string of packets hits some interface somewhere and it's delayed, we don't like that, but it's tolerable if the delay is consistent. In other words, if I know that when I'm talking I have to wait like 1 second for my voice to get there, it's irritating, but I can still maintain a conversation. So the delay, we don't want it, but if we're going to have it, as long as it's not too big, we can deal with it. Jitter, on the other hand, is really bad. Jitter means, okay, jitter means something like this, where I've got a string of packets, and maybe the first few packets have this much delay in between them, but now I got a couple packets here with a lot more delay in between them. Now I got a couple packets here with very little delay. Now I got some big, so the delay in between the packets is random. It's variable. It's not consistent. And where that shows up in a voice call is where where someone's talking to you, but because the delay is variable, as you're trying to listen to them, it sounds like, and hello, and then I walked to the car, and then I saw my dog. You can't even tell what you're listening to, because as the packets are coming in, the IP phone can't reconstruct them into a legible conversation because they're coming in with variable spaces in between them. That's jitter, and jitter is very bad. QoS can manage that. QoS can hopefully prevent jitter from happening. And loss or drops. Hopefully, QoS can prevent packets from being dropped. But if stuff has to be dropped, now with QoS we can manage what will be dropped and what won't. So that concludes this video on an introduction to QoS.